Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem number 2290, minimum obstacle removal to reach corner. It is a graph-based problem and asked in Google recently. Also, Google is known for asking graph and DP problems in their coding interviews. It is also marked as hard, but don't worry about that because these problems like based out of graph data structure are mostly involving conceptual knowledge rather than involving some kind of tricks. So if you know the concepts very well, these problems are not that hard to you. Here's the problem statement. You are given 0 index to the integer array grid of size m cross n, and each cell has one of the two values, either 0 or 1. 0 is representing an empty cell and 1 is representing an obstacle that may be removed. And in the grid, we can move in any of the direction, up, down, left, right. These four directions are allowed to us. What we have to return from the function is minimum number of obstacles to be removed so that we can reach from top left to lower right corner, from 0, 0 to m-1, n-1. If you have a look on this example, this is the grid given to us. It is an m cross n grid. We have to start at 0, 0 and reach m-1, n-1. And we have to return the minimum number of obstacles that we have to remove to be able to reach from source to destination. Let's say in this grid, there is no valid path if we are not allowed to remove the obstacle. Let's say if I remove these two obstacles, in that case, there will be one valid path like this. And I can remove these two obstacles as well. But the minimum possibility that we can remove is 2. We have to remove at least 2 obstacles to be able to reach from source to destination. We are not bothered about the length of the path, any kind of thing. We don't have to keep in mind. Just consider that the obstacle should be minimum. And the grid will be given in this form. 0 for empty cell and 1 for obstacle. So how we can solve this problem? We definitely have to start from 0, 0 and reach this destination. So that is final. So it means the path should be valid. And along that path, we have to get the minimum number of obstacles. So why don't I just check all the paths from source to destination? If I check all the paths from source to destination, I will keep track of the number of obstacles encountered along that path. And in the end, among all of those captured valid paths, I will just see whatever the minimum value of the number of obstacles on any path. So for that, what I can do is I will just directly use DFS here in this case and getting path from source to destination. And on every path, in the end, when I'm reaching the destination, I will capture the minimum value. Minimum value is the number of obstacles encountered during that path. So in the end, I will be having that answer. So this is a recursive approach, checking all the valid paths and counting the obstacle along that path. In the end, return the minimum obstacle encountered in any valid path. Valid path is that we are able to reach to the destination, which is m-1, n-1. If I show you code of this approach, it will be like this. Here in the code, in the main function, I am calling my solution or helper function. Helper function, I am passing the initial coordinates. Initial coordinates are always going to be 0, 0 and a boolean array to keep track of the visited cell, that we are not coming back to the same path again. And 0 is the number of obstacles in that path. So whenever the path is ending, it means we are crossing the limit or we are encountering going on a visited cell, then we will just directly return. If we have reached the destination, it means we have come through a valid path with covering some obstacles, and those obstacle count will be in this OBS variable. So OBS variable will be compared with the global minimum variable, and I will just get the answer. And if it is not a destination or not a terminating case, then definitely this cell can be the part of my path. So I will mark this current cell visited, and if it is an obstacle, I will just increment the obstacle count and go to all the directions. And ultimately I will do the backtracking because to check other possibilities as well. So this is nothing. I just did the DFS starting from 0, 0 index to n-1 index. But here, if I look on the constraints are quite high. M and n value are 10 to the power 5. So if I run over sample test cases, it is going to working fine. But when I submit the problem on a bigger cases, it is going to give me TLE. Even in this recursive solution, I add the memorization, taking a DP array and DP array initializing with the maximum value in the starting. and if any call, if the current obstacle is greater than the already captured value, then discard that call. Even after doing the memorization, if I try to submit again, it is still getting me TLE on very large cases like this. So we definitely have to use some better algorithm here. So our brute force is working fine, but it is giving us TLE on the large cases. So how do we handle that? In the problem, we have to go from source to destination, covering the path which is having minimum obstacles. As this is a graph representation, I can assign weight to my graph edges as per the type of node we are encountering. If we are encountering an empty cell, we can keep our cost 0. If we are encountering an obstacle, we can keep the cost of that portion of the path as 1. So let's say we are at cell 1, 2 and we want to go to cell 2, 2. In that case, the cost is going to be 0. And if I am at 0, 0 and I want to go to 0, 1, in that case, I will consider my cost as 1. So this edge will have a weight of 1. This edge is having a weight of 0. So what I have done is I have converted this graph in a weighted directional graph where every edge from U to V is going to have some kind of weight. And the value of that weight can either be 0 or 1. If we are jumping on a obstacle, then the weight will be 1. If we are moving on an empty cell, then the weight is 0. So now the problem has changed to this one. We have to go from source to destination in a weighted directional graph where the cost of the path should be minimum. When we have to minimize the cost of the path in a directed weighted graph, we use Dijkstra algorithm. What Dijkstra algorithm does is, let's say I have considered these two paths from source. It will decide what path to pick as per the cost. So in this case, both the paths are having one cost. It will pick any one of those. So let's say if this is the case, 0, 1, 1, 0, 1, 0, 1, 1, 0. If this was the case, when we are at first cell, we can have two possibilities, either going here, either going here. If I go here on the obstacle, the cost is 1. If I go to 0 cell, empty cell, the cost is 0. So in the next step, it is going to pick this one first and this one will come later in the priority queue. So that priority queue is going to be in the increasing order of cost, or you can say number of obstacle we have encountered during the path. So we use priority queue to check the next path step and keeping the cost minimum in this case. In this way, we will be able to optimize our path hunting from source to destination, which is having minimum obstacles. Let me give you a brief of how we follow the path in Dijkstra algorithm. We are clear that we go from source to destination and we find the minimum cost path. Our source is definitely on 0, 0 here as per the problem statement. So 0, 0 I'm going to add in the priority queue. Along with the indices of the cell, I also need to add one parameter, which is the current cost of the path, or you can say the number of obstacle on the path. Here we have 0. So this is in the priority queue. And what we do here is we'll just get one element from the priority queue. This element we have got from the priority queue and we'll check all the neighbors of it. Its neighbors are this one and this one. The right one neighbor, 0, 1 neighbor is of weight 1 because it is an obstacle. And 1, 0 neighbor is of weight 0 because there is no obstacle in it. Okay, these two elements are inserted and now this was discarded. Now we have to pick one element from the priority queue, and my priority queue is going to be in the order of increasing cost, which is 0. It's increasing number of obstacles. So I'm going to pick this element from the priority queue, and here I will check all the neighbors. What are the neighbors? Neighbors are 1, 1 and 2, 0. On 1, 1, if I go from here, what is the cost? Cost here is 1 because initially cost was 0 plus 1, it is an obstacle, so it will be 1. Similar to this one. So now we have this state, and now we have to extract one more element, pole 1 element from the priority queue. This can be anything. Let's say it is this one, 1, 1. I can go in the 4 directions, and all those 4 directions I'm going to put in my priority queue. And let's say if I put this direction, this is 1, 2, and now what is the weight? weight is going to be 1 plus 0, which is 1. So overall, this is the weight if I follow this path, coming like this. And I will add other elements as well. This element is going to have 0, 2, 1, and the weight is going to be 2. So this will be in the later part of the priority queue, and these will be in the front. This one, and this one. And next time when we have to pick an element, the element will be picked from among these three. So let's say if I pick this one, 1, 2, and 0, I have picked this one. If I go down, it will be 2, 2, and the cost is 1. Okay, and now here indices are 2, 2, which is our destination. So this is my destination, and the cost till this destination is going to be my answer. So in this case, the answer would be, if I follow this path, going down, then right, then down, we have only one obstacle, which is this one. So 1 is going to be the path. If I remove one obstacle from this path, I will be able to reach to the destination. So minimum obstacle removed to reach destination is 1 in this case. So this is how usually the Dijkstra algorithm works. We use a priority queue, and on that priority queue we have to put the logic, and here the logic is going to be on the increasing order of the cost of the path. Let me show you the code of Dijkstra algorithm. In Dijkstra algorithm, we start from the starting position, which is 0, 0, and we are maintaining a priority queue. Priority queue is going to store integer array. Integer array will have the current cell coordinates, which is I, j, and the cost to come to that particular position from my source. From 0, 0, what is the cost to come to 0, 0? That will be equal to the value at present at the grid. If it is a obstacle, then it will be 1, otherwise 0. Okay. And this is my logic. My logic is that the priority queue will be sorted in the order of increasing order of the cost. And what is cost here is the number of obstacles during that path. So first element is added in the queue. Now I will just poll the current element, and I will check its like neighbor elements. I am polling the current element. The current element obstacle count is this, and row count is this. If the current element is the destination element, then we can just directly return the number of obstacles to reach to this position. Otherwise, move to all the direction. This is the new row column. If new row column is not a valid, if it is crossing the grid limit, then in that case, I'm just going to continue. Otherwise, what is the new obstacle? If my code is coming to this position, it means the coordinates are valid. This coordinate is going to have either 0 or 1. If it is 1, it is an obstacle. Obstacle will be added to my new obstacle count. Now this is the main logic, and what this logic is going to store is that it is taking care of some DP array. What is DP array? DP array is going to store the value of the cost coming from 0, 0 to current index. Now current index is row and column. Current index is row and column, and this DP row and column is going to store the minimum cost coming from 0, 0 to row column. If that cost is the already captured cost is greater than the new cost, in that case we have found some better cost, so we will update in the DP. Otherwise we'll just discard it. So there is no use for that. We are only going to update the cost in the DP array if we are coming on a better path than the previously captured, and initially all the values are in plus infinity. Okay, so this new obstacle count is better, so we are going to update the new obstacle count and add the current element that we can reach RC from 0, 0 with this new obstacle count. This will add in our queue. Okay, and after processing of this queue, what we are going to have is we will have our DP array filled with what value going from 0, 0 to any particular location, what are the minimum number of cost required. We are starting from 0, 0. From 0, 0 to n-1, n-1 value is going to be captured in this DP variable, DP array. So this value we can directly return, and this will definitely be having minimum number because we are using the Dijkstra algorithm. We are picking every piece of the path from this priority queue, which is the minimum cost path. This is the code for the Dijkstra algorithm. Let's try to submit it. This is submitted successfully. I hope you have understood the problem statement. If something is not clear to you, you can comment down below. I will try to address your questions. Bye bye.